Welcome. My name is Christian Altenhofen and I will now present our work on analyzing and improving the parametrization quality of Catmull-Clark solids for isogeometric analysis. Catmull-Clark solids, or CC solids for short, can be seen as the volumetric extension of Catmull-Clark subdivision surfaces, which are widely used in computer graphics and animation. In contrast to subdivision surfaces or other boundary representations, Catmull-Clark solids describe true volumetric models with internal nodes. The images show three subdivision steps from left to right, and finally the smooth limit volume. However, when using Catmull-Clark solids for physically based simulation via isogeometric analysis, as shown for this engine mount here, the quality of the simulation model is essential. To assess the quality of the CC solid models, we developed a parametrization quality metric that measures the distortion in the limit volume. It measures the distortion introduced by the mapping Fc from the parameter space to Euclidean space. The animations show our quality measure being applied to a CC solid cell inside a larger grid, color-coded from blue, no or low distortion, to red, high distortion. One can see how the distortion increases when the cell gets deformed. These figures show our quality metric being applied to two interactively designed CC solid models, the engine mount model on the left and a tripod model on the right. While the parametrization is distorted around extraordinary edges and vertices, singularities occur especially at the boundary, or more specifically at boundary edges where two boundary faces meet in a single cell. This leads to the determinant of the Jacobian becoming zero and the mapping Fc losing its injectivity, resulting in numerical instabilities and inaccurate results when solving a given simulation problem. In order to resolve these singularities, we developed a splitting scheme that splits these critical boundary cells such that the resulting cells have at most one boundary face. However, due to the hexahedral topology of the CC solid control mesh, cells with just one boundary face must be split as well to maintain a valid topology without T-junctions. As the scheme does not create new vertices on the surface of the CC solid model, its overall shape remains unchanged. This resolves the singularities and drastically improves the parametrization quality at the boundary. However, away from the boundary and especially close to the newly generated extraordinary edges, the distortion has increased. All in all, the parametrization quality of the split model is much better than before. Here we show our results for the tripod model. Splitting the boundary cells resolves the singularities, but slightly decreases the quality throughout the rest of the model due to the larger aspect ratios of the split cells. Bisecting these cells improves the quality again. To assess the impact of our method on the simulation results, we performed isogeometric analysis on four interactively designed CC solid models, solving a linear elasticity problem for each one. The bottom row shows the von Mises stress color-coded from blue to red. As can be seen in the arrow plots, splitting boundary cells and thereby resolving the singularities and improving the parametrization quality also improves the convergence of the simulation results. The split models show smaller deviations from the reference solutions for fewer elements and fewer degrees of freedom. At the same time, the number of iterations required by the solver is increased due to the newly introduced extraordinary edges and vertices. However, the additional iterations can be performed in less time due to the improved parametrization quality, resulting in an almost identical computation time than without the splitting. Compared to tetrahedral FEA, the visual results are almost identical for sufficiently large models. However, for IGA on CC solids, the simulation results converge to the reference solution for much fewer elements and much fewer degrees of freedom compared to linear or higher order tetrahedral FEA. Splitting the CC solid models and thereby improving the parametrization quality further improves their convergence as shown earlier. Thank you very much. For more details on our approach, please refer to our paper.